As we continue our study of statistical inference, I want to teach you about a concept that will soon become quite important to you, and that is the concept of critical values. The steps in hypothesis testing are to postulate a hypothesis about a parameter, use this null hypothesis to create the sampling distribution for the statistic, set a level of confidence, calculate the statistic for the sample, determine where that statistic fits on the sampling distribution, and make a decision. There is an alternative method of hypothesis testing. Let's look at that method. It looks very much like the standard method that you already know. We postulate a hypothesis. We use the null hypothesis to create a sampling distribution for the statistic. We set a level of confidence. We calculate the statistic for the sample. We calculate the test statistic for the sample. We determine where the test statistic fits on the sampling distribution. And we make a decision. Notice that there are several terms and steps here that are different from what we've seen before. What is primarily different is the idea of a test statistic and calculating the test statistic for the sample, finding where the test statistic fits on the sampling distribution, and making a decision based on the value of the test statistic. A test statistic is a transformed value of the observed statistic that can be compared to the values of a standard mathematical distribution. Suppose we obtain the GRE scores for 64 randomly chosen education students who took the GRE. Further, suppose that the average of these GRE scores is 147. Our statistic here is the mean, and the sample mean is equal to 147. One possible test statistic that we can use here is the z-score. Z, you may recall, is a score minus the mean of the score, that is a deviation, that is standardized by the standard deviation. In our case, instead of using a score, we want to use a statistic and take the deviation of the statistic from the mean under the null hypothesis, signified here with mu sub 0. Then we want to divide by the standard deviation of means to obtain a z-score. In the case of our example, that would be the mean of 147 minus a hypothesized mean of 150, and divide it by the standard deviation of the means, which is the standard deviation of the scores divided by the square root of the sample size. If we do this calculation, that equals minus 2.74. So our test statistic for this example is z equals minus 2.74. Now let's talk about how we can use that to conduct a hypothesis test. The standard mathematical model for a z-score is the standard normal distribution. Here's a picture of the standard normal distribution. You may recall that the scores on a standard normal distribution are z-scores. A standard normal distribution is one of many normal distributions and is only special because it has a mean of 0 and a standard deviation of 1. That means that the scores on the distribution are already in standardized units. Here's where our z-score is for our example, at minus 2.74. A critical value is a percentile on a mathematical distribution that demarcates between the region of rejection and retention for the null hypothesis when using a test statistic. What I'm showing you here is a standard normal distribution in which I have marked off two areas, one in each tail. I'm assuming here that alpha, our type 1 error rate, is 0.05 or 5%. Therefore, we need to demarcate so that 2.5% of the area is in one tail of the distribution and 2.5% in the other end of the distribution for a total area of 5%. This area will be known as the rejection region. The bars on this distribution represent the critical values that demarcate between the rejection region and the retention region. The critical values on the standard normal distribution for 95% confidence, that is a type 1 error rate of 5%, are negative 1.96 and positive 1.96. So the values that you see demarcating here between rejection and non-rejection and marking off 5% of the area in the tails of this distribution are the critical values, and there are z-scores that are located at minus 1.96 and plus 1.96. The test statistic is in the rejection region in our example, so we reject the null hypothesis of 150. We calculated a test statistic of minus 2.74. We compare that to the critical values. Minus 2.74 is below minus 1.96, so we'll reject the null hypothesis. If we had obtained a test statistic that is above positive 1.96, we also would have rejected the null hypothesis. For any test statistic that is between minus 1.96 and positive 1.96, we make the decision to retain the null hypothesis. The use of a test statistic and comparing that test statistic to critical values is an alternative way to conduct a hypothesis test. In the next video, I'll show you why this is important.